We are going to look at the basic data types in C and their relationship with the sort of information that can be stored in variable boxes that are declared with these data types. The first one is something that is already familiar. Int is the data type that is used to store information that looks like integers, like 156, -3, etc. Float is something that we haven't talked about before. Float is a data type that is used to store information that looks like real numbers, like the value of pi or 2.0, -1.3, etc. We can use float and we can use double. Both of these data types can be used to store real numbers. The difference between double and float is something that we will talk about at greater length later in this video. But basically, the difference is that double occupies twice as much space in the memory of your computer and therefore can store a larger range of numbers. We will, as I said, examine this distinction in more depth further on. A very simple and very commonly used data type is char. Char is the first non-numeric data type that we have encountered. It can be used to print a single letter, a single digit, or a single special character. You cannot print words with this. You cannot print any entity that is larger than one letter or one character using char. And so whenever you assign this or set the value for a char in your code, you will always enclose it in an inverted single comma so that the compiler understands that what is being assigned is a char. So for example, because I have inverted single commas around 2 here, the compiler knows that this is not an int, this is supposed to be a char. These basic data types can also be used with some modifiers, which ends up giving us a large library of derived data types. Modifiers change the normal behavior of a data type and the memory storage space required to store it. For example, the default data type of int, float, or char is signed, which means that the data type can have both positive and negative values. However, it is also possible to specify that we want to use an unsigned int or an unsigned char. Now, what this means is that the data type is guaranteed to only store positive values. Now, why would we do something like this? We will understand this better when we understand how numbers are stored in a computer. And for that, we will have to look at how binary representation works. And we'll look at that in some lectures further down the road. But for now, let's just talk about the other two modifiers that are possible to use. We use short with the int. We can also use long with an int. And both of these directly modify the memory size of the normal int. Short uses half the memory size of a normal int. Long uses twice the memory size of a normal int. And so the bigger size you have for your int box, the larger range of values it can store of that type. So you can see that this product of modifiers with the basic data types int, double, float, and char gives rise to a large library of possible data types. Each of these has a specific placeholder specifier rather, that is used in scanf and printf for the compiler to know the nature of the information that is to be stored in these boxes and that is to be printed. So for example, for int, all of these are plausible data types derived from the basic int. You can have a signed or an unsigned int. You can have a short or a long int. You can have a combination of short unsigned and long unsigned. So multiple modifiers are also possible. Similarly, you can have a float, you can have a double, you can have a long double. These are all possible variations on float. You can have a char and you can have an unsigned char. These are all possible modifications of char. So this is a great way of trying to understand the logic behind this library, that these are all modifiers interacting with a small number of basic data types, int, float, and char, that gives you this big zoo. And don't bother remembering the placeholder specifiers for this. I will allow you to bring that cheat sheet in your final exam, and in your assignments and so on, you will always be able to use the web. So I wouldn't worry very much about trying to memorize these. Before we move on and look at the more exotic data types, let us quickly deepen our understanding of int. Something that you haven't noticed about int, but that will be obvious once you think about it, is that it cannot store an infinite number of integers. Integers go from minus infinity to plus infinity, but no computer with finite memory can store an infinitely big number, right? So there has to be a limit to how big a number can be stored in a memory unit of a certain size. Now, if you have 1 bit of memory storage, and that bit can take a value of 0 or 1 in binary code, then what is the number of values that can be represented in that 1 bit of memory? It can either be 0 or it can be 1. So at most 2 pieces of information can be represented using 1 bit of information. Similarly, if you have 2 bits worth of space, then you can store at most one of 4 unique values: 0, 0, 0, 1, 1, 0, or 1, 1. You can store any one of these 4 combinations in that 2-bit set. Similarly, if you have 3 bits available, your dictionary of possible values expands to 8, 2 to the power 3. So in general, if you have k bits of space available, you can represent at most 2 to the power k values in those k bits of space. So an int on recent 64-bit compilers uses 32 bits of space. That's the equivalent of 4 bytes of space. And therefore, you can store at most 2 to the power 32 integers in an int box. And so to maximize the utility of this int box to store both negative and positive numbers, we basically store its or we basically restrict the range symmetrically to between -2 to the 31 to 2 to the power 31 minus 1. The minus 1 exists because we can store at most 2 to the power 32 values, and we have to store 0 also. So that's why on the positive side, we keep one number less. And 2 to the power 31 minus 2 to the power 31 gives you these numeric ranges that I have listed up top. So that is why the familiar int that we know and love has a limitation on the size of the value that it can store. It cannot store values larger than 2.1 billion, let's say. Now, this is a bit of a blow because in the real world, many numbers bigger than 2.1 billion exist. How do we store those? We'll look at the answer as we go further into our discussion of data types in C. The answer for how we can store long numbers in an int box is to just use a bigger sized box. This can be done by modifying int using long. And with long, you get to use 64 bits of space, 8 bytes of space instead of 32 bytes, 32 bits of space. And this allows you to store values from minus 2 to the 63 to 2 to the 63 minus 1. And you can see that because this is exponentials that we're talking about, the expansion in range is actually considerable, such that you can store numbers in the range of not billions, not trillions, not quadrillions. You can store up to 9 quintillion numbers. And this is pretty good. And for real world numbers, this seems like a decent sized range. Everything above this is can be approximated. So what you do when you want to store long ints is you simply specify long a. You can say long int a also. That is also allowed by the compiler, but you can just say long also, and the compiler understands what you're trying to say. And the placeholder for this is percentage %LD. So D is for integer and L is for long, just for your reference. You scan it, you can print it, and it will return 0 as usual. And it will put a huge number inside this box, which is called A, but instead of the regular int, which occupies 4 bytes of memory, this one will be occupying 8 bytes of memory in the computer and storing much, much bigger numbers. So, integer arithmetic, as we saw in the other video that we've posted this week on arithmetic operators, all of those operations apply to long int as well as int. And feel free to try them out on Pruter. And the question that you'll be asking is, how does long play with int? What happens when you try to add an int to a long, or when you try to multiply int to a long? So when you do this, what happens is something called implicit typecasting. And this can be a little bit complex. It has some rules that you have to remember. And we will talk about typecasting, both explicit and implicit, in a different video, but not here.